Welcome to another podcast. In this episode, we're going to be taking a look at power series representations. This is a catch-up lecture that you're going to work on over Thanksgiving break. There is a bonus quiz associated with this lecture. The bonus quiz will cover part of this power series representation stuff, and it will also cover part of the interval of convergence and radius of convergence of power series that we talked about in class on Monday before the break. So I want to start this by just kind of calmly reviewing something we discussed in class, and that is if you look at the function f of x equal 1 over 1 minus x, this has a resemblance to our geometric sum formula, which, if you recall, the geometric sum was the sum as n goes from 0 to infinity of a r to the n, having a sum of a over 1 minus r. We used this in class to say, well, 1 over 1 minus x looks a lot like a over 1 minus r. In fact, if I was thinking of it that way, then a would be 1 and r would be x. So it seems logical to think that the function 1 over 1 minus x could be represented as a sum of the form n goes from 0 to infinity of, if a is 1, you would have 1 times r x to the n, which is 1 plus x squared, and so on. And that is indeed the case, that this function has a representation in terms of a power series. The representation then is the sum of these two guys. Looks like this. And so the idea is that this is called our power series representation. And it turns out that a lot of functions have power series representations. We're going to explore a lot of those in this lecture, and then we're also going to explore an extension of this called a Taylor series in the lecture on Monday before our exam on Wednesday. So we can kind of put off to the side if we want. We have this basic relationship that f of x equals 1 over 1 minus x is given to us by a power series of the form n goes from 0 to infinity of x to the n. And we're going to use that relationship to come up with several more power series representations. All right, so let me clear this out, and then we're going to look at several examples. All right, we're going to start first by looking at a sum that's based off of this, of the form. Let's see here. The first sum we're going to look at, going to do a simple one. So here's our first example. We're going to look at f of x equal 1 over, let's say, 5 plus x. All right, can I compare it to this function? And I just want us to recall from class that this relationship, this pairing, works as long as the absolute value of x was less than 1, because it's based off of the geometric series, which is convergent as long as the common ratio, which in this case is x, is less than 1 in absolute value. So the idea for these problems is going to be to make each of these look like 1 over 1 minus x. So I want this to look like 1 over 1 minus something. And the easiest way to start with that is to think of 1 over 5 plus x is to divide both the top and bottom by 5, because in doing so, I have the 5 will turn into a 1 like I need it to there. So this is going to be 1/5. Dividing by 5, I get 1 plus x divided by 5. Okay, I'm going to pull the 1/5 out of the top, in which case this is 1 over 1 minus negative x over 5. So you can see that when I have it in this form, I can immediately point to the fact that a is 1/5, r is minus x over 5, And so if I use the same idea that I used to come up with the geometric function 1 over 1 minus x, then I can express the function 1 over 5 plus x as being the sum n goes from 0 to infinity of a times r raised to the n. And in fact, that's how I do want to handle this. We'll probably clean this up a little bit. Probably a better final form here would be to combine the 5s and separate out the negative. So this is an alternating series because of the negative. You'll have negative 1 to the n, x to the n, over, there's two 5s, you're going to get 5 n 5s and then 1 5. So this is 5 to the n plus 1. So this is another power series representation. I can represent the function 1 over 5 plus x with the series that I have here, this alternating series. All right, let's take a look at another example. This one's going to be slightly more involved, but I want to look at the function x to the 5th over 7 minus 9x cubed. So even though this looks a little bit scarier, the premise is exactly the same. Can I get this to look like a over 1 minus something? Just like here, I wanted it to look like 1 over 1 minus something, but really it's a over 1 minus something. The a in this case turned out to be 1/5 that I pulled out of the top. All right, the obvious thing to do here would be to proceed just like I did here. I want a 1 in this position here, so I divided by 5. I currently have a 7 in this position, so I'm going to divide by 7. So if I divide the top and bottom by 7, the function becomes x to the 5th divided by 7 over 1 minus, and here I've got 9/7 x cubed. So every piece gets divided by 7. All right, I'm going to pull out the x to the 5th over 7 term, and it's multiplied by 1 over 1 minus this 9/7 x cubed term. So it looks to me like a is x to the 5th over 7, and r is 9/7 x cubed. So if I kind of try to put that all together, then both of these would suggest that the sum I should look at would be the sum n goes from 0 to infinity of a times r raised to the n. And this looks good. In fact, I could pull the x to the 5th out if I wanted to, but I'm just going to try to combine everything here. That's typically how we write our final answers. So the 9 here is raised to the n power. Be very careful about that. So you have 9 to the n. You have x to the 5th and x to the 3n. So this is x to the 3n plus 5. If you add up all the exponents here, you have 3n x's here and you have 5 here, so you have 3n plus 5 total. Across the denominator, you've got just 1 7 here, and you've got n 7s here, so you have 7 to the n plus 1 in the denominator. So this is another power series representation. I can represent the function x to the 5th over 7 minus 9x cubed. I can recognize it as being this sum, 9 to the n x to the 3n plus 5 over 7n plus 1. Now, the question that we have been sort of avoiding here is what happens to this interval of convergence? So for instance, what I mean by what happens to the radius of convergence is, the radius of convergence here was the absolute value of x less than 1, but here and in general, if you have the sum, n goes from 0 to infinity of a r to the n, this converged when the absolute value of r is less than 1. So here r is negative x to the 5th, so this first series that we worked will converge when the absolute value of r is less than 1, but that's the same thing as the absolute value of x is less than 5. So the radius of convergence for this first example is r equal to 5. The interval of convergence then would be, it's based on the center point, and the center point here is at 0, so it's centered at 0. So we would have from minus 5 to 5. And the idea at that point would be, does it include the endpoints? Well, I can check real quick here. If I plug in negative 5 for x, or if I plug in 5 for x, both of these are going to diverge. It just gets rid of too much, and it won't pass the alternating series test in either case. So the idea there is that our interval of convergence is this for this series. In other words, if I want to use the function 1 over 5 plus x and have this sum approximate it, I can only do that between minus 5 and 5. All right, what about down here? Well, down here, our ratio is 9/7 x cubed. So I got to keep 9/7 x cubed less than 1 in absolute value. But if I do a little bit of algebra here, that's the same thing as x cubed in absolute value less than 7/9, or x in absolute value less than the cube root of 7/9. So my interval of convergence here will be from minus the cube root of 7/9 to plus the cube root of 7/9. And I'm not going to include the endpoints here either, because you can see here that when I update this at either of those values, this is going to be divergent outside of this, because you got a 9/7 here, as opposed to what you get with this one, which would diverge because it wouldn't pass the divergence test. This would diverge because it would be a divergent geometric series at that point. So the idea here is I have to update my radius of convergence and interval of convergence when I do this process. It's not going to stay this absolute value of x less than 1. It's going to change based on whatever the r, whatever the common ratio is that we used in this process. Now, this is only an explanation of what happens for using this trick of taking the geometric series and the geometric function and then expressing other functions that look like it in terms of the geometric sum. We're going to look at a couple more examples here where we're going to kind of branch outside this and observe what happens when we add derivatives and integrals to the mix. All right, welcome back. We're going to be continuing our thought process here for power series representations by trying to expand a little bit of the technique that we just introduced. The idea here is that we're trying to establish a link between functions and power series. And I'm just going to show you the most general form of a power series where it could be centered at any point. The point where it's centered, so remember x naught is called our center. It's the place we most want to approximate the function f of x at. Right, so we're going to place the center point of our approximations near places where we're really interested in what the function f of x is doing. But the best we've been able to manage so far is functions that are related to 1 over 1 minus x. We haven't been able to stray really far from that because right now the only good power series that we know is this geometric series relationship, recalling that it converged when the absolute value of x is less than 1. So this is the only thing we've had going for us in terms of coming up with power series representations. Well, I want to add a couple of more things that can kind of help. So let's consider a function that's of this form. So it's of the form a0 plus a1 x minus x naught. I'll write out a couple more terms. But basically it has this power series expansion. there's a couple of really nice properties that the function must have in order to have a power series expansion. So I'll say the first thing that comes from this is if f of x has a power series expansion of this form, then f of x is differentiable, which means it's continuous. Remember, if a function is differentiable, it's also continuous. On the interval from x naught minus r to x naught plus r. In other words, you can go from the center point up to the radius of convergence. So here we would be assuming for this one that it has a radius of convergence of just r in general. For the case of our geometric series, r was 1, but the idea in general is that we have radius of convergence r. So if I have radius of convergence r and my power series is centered at x naught, then I know the function it's representing has to be differentiable and continuous on this interval. And remember, we call this the interval of convergence. So power series representations of functions are continuous and differentiable on their intervals of convergence. When you have a continuous and differentiable function, you should think what happens to the derivative of said function. So we're going to throw out a couple of rules now. The first rule is that if I try to take the derivative, you can see immediately taking the derivative of this, the term a0 is a constant, so I'm going to lose it. And then this term x minus x naught, the derivative of that is 1. So the first term in the differentiated series would be a1. Then we would have 2a2 x minus x naught plus the next term would be, let's see here, the next term would be 3a3 x minus x naught squared, because it was an x minus x naught cubed and I differentiated it to pull the 3 down. The point is, this is the same as the sum of just differentiating inside the series itself. So the derivative of x minus x naught to the n is n times the an that's already there, x minus x naught to the n minus 1. And because I lost the very first term of my power series when I differentiated, I lost a0, then the first term won't be a0, it'll be a1, which means my sum will start at 1 instead of starting at 0 like this one did. So this is called the differentiated series. And what I want you to get out of this is this basic relationship. If you have a function that has a power series representation, and I'll do the general one centered at x naught, then the derivative of that function is the same as taking the derivative of the power series. But what this property says is you can simply take and put the derivative inside the power series. You can move it inside the series. When this comes inside the series, you lose the first term where you differentiated it away, and then all you do is take the derivative of the terms that are left. And so the terms that are left, when you take their derivative, you ignore an, it doesn't have an x, and then x minus x naught to the n is x minus x naught to the n minus 1. And so this explains how you can do the operation of differentiation on a power series. Very important result. This whole process or explanation that I'm giving is what's known as term-wise differentiation. So if you have a power series representation of a function, then you can obtain the power series representation for that function's derivative by term-wise differentiating the original power series. And as you might expect, this carries over to integration as well. So if I wanted to look at the integral of my function, and I look at its power series, then the integral of a0 would be a0x plus, I would get a1 x minus x naught, this would be squared, divided by 2 plus, and you get the point, I would integrate each term, but I would also produce a constant of integration. And the constant of integration is something that we're going to have to figure out after the fact once we've come up with what our integrated series is going to represent. But the point is, you can write this as the series going from n equals 0 to infinity of a n x minus x naught to the n. And what this says is I can move the integral inside the sum and integrate term-wise. The integral here is with respect to x. And in doing so, I don't lose a term of my series. This doesn't go to n equal 1 like the derivative did, because the idea there is that I'm not losing the term a0. It's actually starting at the next term over. So you can see that this is going to be a n x minus x naught to the n plus 1 divided by n plus 1 once I do the antiderivative of this. But then I also get a integration constant plus c. So the integral of the power series representation is given to us by this formula. And just for completeness sake, the derivative of the power series representation is given to us by this formula. Both of these are well worth remembering, and perhaps the most important thing to say here is that the radius of convergence and interval of convergence stay the same, or they're at least as big. So the radius of convergence is as least as big as the original power series for the integrated and differentiated series. Meaning that if this original function had a radius of convergence of r, then I know that my differentiated series has an absolute value of x less than r at least. In this case, because so I didn't take into account when I wrote this, I didn't take into account the center point. The center point is at x naught, so we would write this as x minus x naught less than r. So it has a radius of convergence of r. This has a radius of convergence at least r. It could be bigger than r. In other words, here we didn't include the endpoints. Here we might be able to include the endpoints, and the same thing here. This will have a radius of convergence of at least r. So the question is, how are we going to use this result? Well, we're going to start looking at integrals and derivatives of this function so we can obtain new power series that we didn't have access to before. All right, so let's make use of the termwise integration and differentiation of power series to come up with some new power series. I'm going to start by looking at the function f of x equals 1 over 1 plus x quantity squared. Now, this looks nothing like, well, it's kind of similar to, but it doesn't look exactly like the geometric function that we've used prior, with one exception. We note that if you try to take the derivative of that geometric function, 1 over 1 minus x, it turns out to be 1 over 1 minus x quantity squared, the exact function I'm asking you to look at. So if I wanted a power series representation for this function, then I can just rely on the fact that since this is the derivative of 1 over 1 minus x, then its power series will be the derivative of 1 over 1 minus x's power series, which we know that power series is the geometric series. And I know that the radius of convergence from going from here to here has to be when absolute value of x is less than 1. In other words, that representation is only good for values of x between -1 and 1. I know by the properties of termwise differentiation, I can bring the derivative inside the sum. So I can pass this inside the sum, but when I do, I lose the first term of my series because it's a constant. It gets differentiated to 0. And then I take the derivative of what's inside the series. And in this case, what's inside the series is just x to the n. So this is n x to the n minus 1. So the point of all of this is I can obtain a new power series representation here, and that is the sum, n goes from 1 to infinity, of nx to the n minus 1 will represent this function. So these two things are equivalent. Now, I know based on our previous talk that the absolute value, in other words, the radius of convergence here, is at least 1. I could extend it out to the endpoints, but you notice that if I plug in x equal to 1 or x equal to -1, this series will diverge. So it stays absolute value of x less than 1 for the interval of convergence and radius of convergence. All right, let's look at another example. That's sort of a typical example to start with, but let's look at another one. What if I asked you to explore the function minus natural log of 1 minus x? All right, now that seems peculiar, but I see the 1 minus x, and I'm reminded of the fact that if I take the integral of 1 over 1 minus x, that will be the natural log of 1 minus x. What I'm saying here is I could look at this function, but think of it as the integral of the geometric function, which means that I can replace that geometric function with its power series representation and use termwise integration to move the integral into the sum at a cost of producing an integration constant. There's always a cost. Here the cost is I lost the first term of my sum. Here the cost is I have an integration constant. But the result is I get that this is the sum, n goes from 0 to infinity, of the integral of x to the n is x to the n plus 1 over n plus 1. So this function, minus natural log of 1 minus x, is equivalent to this power series, as long as the absolute value of x stays less than 1. Okay, but does it really have to stay less than 1? If x is equal to 1, this doesn't work, because if I try to plug in x equal to 1, I get natural log of 0. You can see that the sum diverges. So we get a divergence here when x is equal to 1. Thank goodness, because the natural log function, I cannot plug x equal to 1 into that and get an answer. So we wouldn't expect the power series to give us convergence at the point x equal to 1. X equal to -1 is different, though. If I plug x equal to -1 into this function, then I'm going to get the natural log of 2. I'm going to get minus the natural log of 2, which, by the way, is the same thing as, because I can bring the -1 as a power inside, this is the same thing, a natural log of 1/2. And that is a real number. The question is, though, does this power series have -1 in its interval of convergence? We know it's at least less than 1. Can I extend it to -1? Well, here, if I plug -1 in, then this sum becomes the sum, n goes from 0 to infinity, of -1 to the n plus 1 over n plus 1 plus a constant. And what's interesting about this is, what does this constant have to be first? Well, you can see that if x is 0, the function f at 0 is minus the natural log of 1, which is 0. And our power series representation at 0 is, if x is 0, this is gone, and you have 0 plus c. So my power series is equal to 0 plus c. If that's going to be equal to natural log of 1, which is 0, then that implies that c has to be 0. So this integration constant here is actually 0, which means that I'm looking at negative natural log of 2. I could be looking at natural log of 2 instead, in which case it would be the negative of this, since negative natural log of 2 is this. Natural log of 2 is the negative of this sum. Where c is equal to 0. So I have a representation for natural log of 2 here, and the question is, does this converge? Well, yeah, this converges by the alternating series test because the limit of the terms here go to 0. So I have an expression for the number natural log of 2, which, by the way, is an irrational number, has an infinitely repeating decimal, or infinite decimal that doesn't repeat, excuse me. And its power series representation is given to us by this. One last little thing to say here. We've just shown that the natural log of 2 can be written as this sum. If I bring the negative inside, it's just going to give one more negative to go with this. This ends up being the sum. N goes from 0 to infinity of negative 1 to the n plus 2 over n plus 1, which, if I reindex, I'm going to add 1 to the index. I'm going to subtract 1 from the term. This starts at 1 and goes to infinity. Then I reduce all of the term by 1, and I end up with this. So natural log of 2 is given to us by this sum, but if you recognize this sum, this is the alternating harmonic series. So natural log of 2 is equal to the sum of the alternating harmonic series. Who would have guessed? And I know that this is a valid expression because I know x equal to negative 1, which gave us natural log of 2 as an answer, is inside the interval of convergence, because when I plug negative 1 into the sum, I get a convergent sum. I get a sum that converges by the alternating series test. So this is not the last example of doing this, where we take some hard to find approximation to some important number like natural log of 2, and we use a series to approximate it. We know that the convergence happens here at the point x equal to negative 1, so natural log of 2 is valid as a convergence. Let's look at one more example that's very similar to this. Let me just create a little bit of room. All right, and here's what I want to take a look at. I want to look at something that doesn't look at all like 1 over 1 minus x. Doesn't look like it at all. And I want to keep track of all the things we've figured out. So we just earlier we figured out that the function, let's see here, 1 over 1 minus x has its power series representation given to us by the geometric function. We've also figured out that this is its differentiated series. We've also figured out that I could use this to express the natural log function. We just got through doing this one. And now we're going to look at one more function as well. The last function I want to look at is the arctangent function. Now on the surface, this seems like it has absolutely nothing to do with the geometric series. It turns out it actually has quite a lot to do with the geometric series. Recall that the arctangent is the answer to this integral. If I integrate 1 over 1 plus x squared, I get the arctangent. Well, that means then that I can think of arctangent in terms of this integral, but I'm thinking of it in terms of my geometric series now. So I can replace the integrand, the thing inside the integral, with the sum. N goes from 0 to infinity of the ratio r here is negative x squared, so that's going to be raised to the n, and then I'm integrating that series. So let's think about that series for a second. Since r is negative x squared, then this converges as long as negative x squared stays less than 1, which means as long as x stays less than 1. The negative gets absorbed by the absolute value, and then you just take the square root of both sides. So you would have x is less than 1 in absolute value. But this is interesting because I can then do some work on this sum. This becomes, I've got negative here, so this becomes negative 1 to the n, x to the 2n. And we know that we can integrate series termwise, power series termwise. So I'm going to bring the integral inside the sum up until the point I hit an x term, which is the x to the 2n part. The negative 1 to the n I'm just going to pull outside the integral because it doesn't involve x. The cost of doing that, the cost of integrating, remember, is I'm going to produce an integration constant, so don't forget that. If I then integrate termwise, x to the 2n becomes x to the 2n plus 1 divided by 2n plus 1 plus this integration constant. Now, to find the integration constant, I have to think about the function values at certain points in my interval of convergence. And 0 is a common one to use because it's oftentimes we're centering series at 0. We can look at our radius of or we can look at our center point, x equal to 0, and say that they're going to agree at that point. So at the center point, which in this case is 0, my function must match its series representation. The series representation when x equals 0 is 0 for all of this, but plus c. So tangent inverse at 0, this function at the center point must match the power series at the center point. So tangent inverse of 0 is just 0 equals 0 plus c. That forces c to be 0. So I can get rid of this guy and write down my final power series representation given to us by this sum. So I've now got another representation, this time of the inverse tangent or arctangent. Its power series representation, obtained through integration, is this alternating series. This alternating series looks like, if you start plugging in values, it looks like, let's see here, we've got at n equal to 0, we start off with x, I believe, right? So we get x minus, let's see here, the powers are going to go, they're going to be the odd powers, so we get x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. And what's really interesting about this is plugging in values to arctan. For example, what about if x is 1? Can I plug x equal to 1 into this? Well, if you look at x equal to 1, this series at 1 becomes the sum. N goes from 0 to infinity, minus 1 to the n. If x is 1, this is 1, so you get divided by 2n plus 1. This sum would be 1 minus, I'm just plugging in x equal to 1 here, 1 minus 1/3 plus 1/5 minus 1/7, and so on. This actually converges by the alternating series test, so I'm allowed to plug in 1 into my function. But what's interesting about that is, what is tangent inverse of 1? 1 would be an angle whose sine and cosine agree, and that is pi/4. So what we've just sort of amazingly found here is that I can write pi/4 as this alternating sum, because I'm using the function for the powers, I'm using the function arctangent and its power series representation to give us a representation now of pi/4. And this is one of the ways in which this topic, this power series idea, was such an important idea for mathematics. Not only did it allow us to represent functions using sums, which are much easier to work with, but it allowed us also to get our hands on nice approximations to things like pi/4, which is an infinite irrational decimal. It doesn't repeat, so it's hard to get really accurate values of that in a time before we had computers. It's much easier to add up, 10, 20 terms of this to get a really accurate estimation of pi/4 than it would be to do whatever technique they were using prior to that, which were estimations of sorts, but they weren't nearly as good as these. The thing we have to be careful about in all of this, once again, is if I'm going to plug an x value into my sum, and I'm going to use that then as an x value plugged into my function, if I'm going to compare the two, I have to make sure that whatever x value I'm plugging into the sum is inside that sum's interval of convergence. Here we had to check that I'm okay by putting 1 into the sum, because I know that in doing this process, the absolute value of x was less than 1, but because I integrated, it turns out that the radius of convergence, or the interval of convergence, could include more than just -1 to 1, and in fact it does. In fact, what ends up happening here is the interval of convergence for this series is -1 you can't include, because if you include -1 here, actually -1's okay too. So if you include -1, it's okay. But your interval of convergence here includes -1 and 1. Whereas the original series series expression for 1 over 1 plus x squared would only have allowed us to go up to 1 and -1. When I did the integration, it allowed -1 and 1 to work. And so that's an important thing to remember in all this, is how you weave together differentiation, integration, and how that changes radius of convergence, interval of convergence, and then what are the allowed values to stick into the function if I want to use the power series representation of the function. This requires a lot of practice. There are several more videos on this, but it requires a lot of attention to detail. You need to know that when you're plugging a value into a function, that it's an allowed value to plug in. Otherwise, you're going to mess some of these problems up. All right, that pretty much concludes this power series representation lecture. Like I said, I'm going to be going more in depth on this topic on Monday when I look at something called a Taylor series, which is sort of the natural extension of this topic. The bonus quiz is listed online, so take a look at that. It's a shorter quiz than the last one. There's just 2 problems on it, but they're kind of indicative of the types of problems I might ask on the exam. All right, have a great Thanksgiving break, and thank you for listening.